Hello, everybody. My name is Richard Sutton. It's my honor and pleasure to have this opportunity to talk to you today about planning and fundamental questions in artificial intelligence. My title, Gaps in the Foundations of Planning with Approximation. This may seem somewhat, uh, hu- somewhat hubristic, given that I'm not normally thought of as a planning researcher. To talk about the foundations may be hubristic. You probably think of me more as a reinforcement learning researcher, but reinforcement learning involves all the aspects of intelligence, and so it involves planning. Planning is a fundamental part of AI. It's it's appropriate to try to think about the fundamental questions, and so I'd appreciate if you would take my comments as not so much being arrogant as much being ambitious and viciously trying to talk about the things that are really important for all aspects of our field. So I need to spend a bit of time talking about what we mean by planning so that we can get on the same page. Um, so in reinforcement learning, we think of planning as most naturally as dynamic programming, or in particular, value iteration with a model that we've learned from the world. And from this point of view, I see five big challenges to extending this value iteration approach to the goals of AI while keeping it simple and general and scalable and efficient as all of our methods need to be in order to be relevant. And for of these five challenges, four of them, to me, it seems like the way forward is reasonably clear. Those four being the introduction of average reward, partial observability, temporal abstraction, and function approximation. Now, um, when I say it seems clear, I mean it seems clear to me, and uh, so I'll be explaining to you how I see it, and hopefully, some of you may agree right away, and some of you may see things differently, and that's in some sense the point and the potential value of this talk. That it will give us a way of of talking to each other and exchanging opinions and ideas, so we can have a good discussion of those issues. And there should be time to do that uh, today. Now, of these five challenges, the fifth one still remains genuinely uh, unclear to me, unclear about how we should move forward. And the fifth one is some sense what might seem like it's the smallest. It's just having to deal with stochastic transitions, given that we have an approximate model of the world. So that's my outline. Let's get started. And as I say, we have to get started by talking uh, about the basics and making sure we know what we mean when we use the words. So I'm going to tell you what I mean by planning. Planning, I just mean any way of using a model of the world plus computation and not experience, not data, just the model computation to improve a decision-making policy or the value function that leads to a decision-making policy. Planning is a model of the world, using a model of the world. The model of the world, you might call that knowledge. Anyway, you take knowledge, the model, plus computation to improve your behavior. If you just go to psychology or just think about common sense views of the mind, of intelligence, it's common to think of it as consisting of two parts, a fast part and a slow part. The fast part giving you reactions, giving you intuitions, and then the slower part that hopefully will make better choices, but is slower and combines more of your background knowledge. Um, so the second part is obviously what we mean by is where planning takes place. Um, but planning has to take place within the overall context of acting rapidly and occasionally um, thinking more slowly and better. So these two phases, or these two parts of the mind, I think of them as the reactive foreground and the deliberative background. In psychology, Daniel Kahneman famously called them System One and System Two in his best-selling book, Thinking Fast and Slow. We're familiar with this. In robotics, we often have the controller who controls the moment torques of the robot, and then a trajectory planner. And that's also the same kind of division between a fast part and a slow part. The slow part being the place where planning occurs. Okay, um, now let's talk about how we talk about these things, these same things in reinforcement learning. We also talk about the fast part and the slow part. So, but in reinforcement learning, the setting is that an agent is interacting with the world, usually discrete time steps. And the interaction consists of taking actions, receiving states, and also rewards, where the objective is to maximize the rewards. And then we will both learn and we'll plan. And the learning part is the agent uses experience to learn a reactive policy and map from states to actions, and a value function that maps states to predictions of future reward. And third, in a model-based reinforcement learning, we also learn a model that maps states and actions to what we expect to happen, the expected rewards, and a distribution over the possible next states. So once we have the model, we can consider doing planning, where the agent uses the model and computation with no new data to improve the policy and the value function. So this brings us at last to a specific algorithm. That is the algorithm of value iteration, which is the most natural way to look at planning in reinforcement learning. And this is an important equation, and I'm just going to have different variations on this equation throughout the talk. So it's kind of important for us to understand it. Um, so let's spend a little time on it. Let's start with the model. The model uh, is up in the upper right-hand corner in purple. It takes a state and an action, produces a probability distribution over the next state, which we'll often call S prime, and the expected immediate reward, R hat. Okay, so that's the model. And then we're going to use this, and we're going to use it in a very incremental way. Whenever we have time to do some planning, we will just select a state out of all the possible states that we might think about. And this is an important choice. What state do we think about? Yeah. So we're going to call it search control, and then we're going to spend no more time on it. It's really important, but we can't do everything. And it's going to be orthogonal to all the things that I'm going to talk about today. So let's just mark that up as something that's going to be important, but I'm not going to directly deal with today. At each state that we select, we're going to perform a backup, what I call a backup, which is an update of the estimated value of that state. And this is in the most simple case of dynamic programming planning, which is value iteration. Value iteration actually only updates values, and then the values would be used to help determine good actions. But we can consider it's adequate for our purposes today to just consider the value update. So now consider the diagram. I guess from the equation, you can see that I'm going to change the estimated value, capital V of S, for the state S that we've selected. And then the way this equation should be interpreted is perhaps best understood by using the diagram on the right. The diagram on the right shows at the top is the state we're going to update, and the green line is suggesting that update. Something happening at the bottom, we're going to use to update the value of the state at the top. So from that state, we'll have many possible actions we can consider. We're going to take the max of them because we're trying to consider what action we should do. We want to consider we're taking our best action. So when we consider each possible action, we consider the reward, expected reward if we take that action. And then we have to consider all the possible um, next states S prime that might result in its probability. So that's the second branch. The backup tree has two branches. Each and every elementary primitive backup at a single state has two branches. And those two branches we see now in the equation as being the one branch is the max. We take the max of our actions. And the other branch is the sum, where we consider the sum over all possible next states. So now let's read the equation. The estimated value of the state S is changed to be the max over possible actions that might be taken in state S. And then we consider the expected reward and the probability, and then we consider a, well, gamma. Gamma is the discount rate. So this is normally the most common way of doing value iteration. It's in a discounted framework where rewards that are imminent, that are immediate, are given the most weight, and delayed rewards are given less weight according to gamma. So you might think of just gamma as like zero point 0.9 or 0.99, a number that's near 1. Okay, so we have the immediate expected reward, and then we have the sum over all possible next states. How likely is each next state to happen, given that we are in this state and do this action? And then what's the value of that next state? So that the whole thing in the sum is sort of like the expected value of the next state. And that combined with the expected reward, taking the best of the choices, it is the new estimated value of the state in question. So this is a sort of prototypical planning operation. It's not that different from tree search. In fact, you can do tree search if you just do these backups in a particular order. The same kind of backups happen in Monte Carlo tree search and A star. This way of doing it is as individual sort of uh, single step backups rather than predictions about strings of future possibilities is just a really convenient way to do it in 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 reinforcement learning and in general. I think uh, it, it's I think it's representative of of what one might do, and I think it will be enough for us to make some interesting statements. So um, I actually am intrigued by the idea that planning might work literally this way, that it consists entirely of these one or two half-step look-aheads. But it's what I'm going to say will be consistent with other views as well. Okay, so now let's consider the extensions. The five possible extensions is sort of the outline of the rest of the talk. Um, you see the extensions listed on the right. So these are five extensions to make valuation more realistic and powerful, more AI capable. There are also five major branch points in your research, possible research. There are also five challenges and five tests of our ambition and our courage as we uh, embrace these challenges and try to solve them while remaining simple, scalable, general, and computationally efficient. Okay, so this is what we're going to talk about today, these five. And the first four are the ones that I think we have a reasonable plan for solving: average reward, partial observability, temporal abstraction, and function approximation. And then the last one, we'll talk about stochastic transitions and why that's particularly challenging. Okay, so let's get started. Average reward. This is about moving beyond discounting because uh, discounting is problematic in many ways. And the most basic way is that once you introduce function approximation, it's actually the, the problem formulation becomes broken. We can no longer talk about doing the best in every state. We have to pay attention to which states we actually encounter or are otherwise interested in. Um, so the common approach is to do discounting or to introduce episodes. Life doesn't have episodes, uh, and discounting is not really satisfactory. Um, I want you to notice the great appeal of simply maximizing the average reward per step. This is this is the most natural thing in the world. You want to get the most reward per step as time goes on. You don't want to discount. If you want to discount, you can handle that in other ways. If you think there's a probability of the game ending, well, you can include that in your dynamics of the world. You don't have to include it in the problem formulation. The problem formulation is very naturally formulated as average reward per step. And there are theoretical reasons why it actually isn't sound the way it is typically often done with discounting. So, without belaboring the point anymore, uh, I want to tell you that we really should be doing average reward, and it's high time that we did it. And it's not that hard. It's not it's sort of easy. I originally thought it was very easy, and it was just a question of looking up in the dynamic programming literature and find out how they did value iteration with average reward as opposed to discounting. It's a very established thing. It was worked out in the 60s, and I thought it would just be a question of looking that up and then generalizing our discounted value iteration to the average reward value iteration. But although there are methods from the 60s, they're not really well suited for AI, for reinforcement learning. They don't work well in asynchronous incremental settings. Um, so uh, some interesting additional research is needed to devise new methods, and maybe that's been done now. Just in the last year, we have an ICML paper. This is the paper here mentioned by Juan, uh, Nake, and myself, ICML 2021, where we present learning and planning algorithms for the average reward case. The basic idea, though, is what you see here in these on the right hand side. So the conventional valuation equation we have just been discussing is shown, and I'm showing in red the things that are going to change. So we're going to get rid of the discount rate parameter. That will just be removed, and it will be replaced by R bar, which is an estimate of the average reward rate. We're going to have to learn this separately, R bar, but otherwise well, basically we're looking at the rewards that we expect to get because I'm taking this action, and we'll compare it to the long-term average reward rate, R bar. And then R bar is just a scalar that we'll also have to estimate, and it will be estimated by a very similar kind of update equation that you see below. Okay, so if we do these things, we can manage average reward and we can get past this challenge. Not that there's anything more to be worked out and shown, but I think this is the way forward. And notice that this things in red are changed or new. We're going to follow this convention as we go through the 5 challenges. Second challenge, partial observability. So the challenge is that really the world doesn't give us states, Markov states. It really just gives us data. It gives us observations. So the agent is responsible for creating state from the observations and actions. The way to do this is stated generically as a state update equation. You have to compute the new state as some function here called u that takes the old state, the latest action, and the latest observation, and produces the new state. So this, this process of updating the state has to be done as part of the fast part of intelligence, the fast part of the mind. It's because you need the state on every step in order to take your actions. And so as fast as you take actions, you have to update your state. Now, so really we're going to be working with the state of that the agent has created, not the state of the world. And the created state is not going to be Markov for the world. The world here being in these pictures being written as M for environment. Okay, so if we look at the picture, we have the standard original case where the environment of the world delivers states to the agent. Now the environment will deliver observations, and then the observations will be processed by you, the update function, along with the actions in the last state to produce the state. And now in this way, we have reduced the new case with observations to the old case with states because the rest of the agent can be just as before because now are sending states to it. And so it doesn't really have to know that those states came from an update function rather than directly from the world. And so I'm really pleased with this outcome that we can reutilize everything we learned about agents working with states. We don't have to change anything really in order to handle partial observability. Now, it's common to change things a lot, and that's what I'm really offering as an improvement or a better way to think about things. Um, we're going to keep the observations limited to the generation of state, and they're not going to be involved in, say, the model of the world. Everything after inside the agent, for example, the model building, will just work with states. One way this is quite important is once you bring in temporal abstraction. Um, it's all part of resisting the appeal, the siren call of modeling the world at a single step. So we should realize, first of all, that life is lived at the small level, one muscle twitch at a time, one fast action selection, one fast new sensory input, one time step, a small time step at a time. But planning, of course, has to operate at higher levels. Planning may be important at a fine level, but it's also very important at larger levels. You have to think not just about how to twitch your muscles, but also how to uh, plan your day or plan your career, to open a door or walk to work or call your friend on the telephone. All of these actions are consist of many actions, hundreds, some cases thousands or millions of actions, small actions, and yet we can plan with them um, seemingly in a very similar way as we at different levels in perhaps a hierarchy. So our knowledge of the world is at a higher scale, and it's also not conditional on single actions. It's conditional on whole ways of behaving. If you consider walking to work, well, that involves um, a whole way of behaving. If you consider taking a new job, well, that involves a whole new way of behaving. And so the normal way of formulating these things has the name, the jargon name, options. An option is just a policy and a way for the policy potentially ending. So the model of an option is going to be just like before, but it's with a temporally abstract semantic. So we see on the right now, the conventional model takes in an action and produces a distribution over the next state. And those two things in red are going to change. When we go to an option model, we're going to take in an option rather than action, and we're going to give a probability distribution over the state at which the option stops. Okay, so that temporal part that you could stop like when you walk to work, when you get to work, or if you're trying to open the door, then it stops when you open the door or you find it's locked. So it will be many steps later, but it's still probably probability distribution over the outcome state of the option as opposed to the outcome state of the action. Now the rewards also have to be treated slightly differently. Instead of taking the immediate reward for doing the action, you have to take the total reward over the time period which the option is in effect. So you have to sum it up until stopping. And then it's nice because actually, if you formulate things this way, um, value iteration is unchanged. You can do the same equation, you're just going to write O instead of A because you have possible options in every state. The options will include the primitive actions, but also larger things. So you sort of enlarge the action set, and otherwise, value iteration is unchanged. Now you notice I'm still using gamma here. That's just my choice for presentation. We could have converted, we could have done all of the five challenges and their possible solutions cumulatively, but I'm doing them one at a time. But they do naturally combine. If you were to do um, an average reward formulation, you could do that average reward formulation with options by doing extension in the same way. Now, I mentioned the one-step trap and why uh, you why it's problematic and why it's a trap to think of your models as one step and to think of um, the partial observability being treated uh, by one-step solutions that involve uh, imagining possible options. Excuse me, possible observations. So that really what the one-step trap is. The one-step trap is thinking that you can make do with one-step predictions, thinking that you can predict the state of an observation one step later, and then you can make longer-term predictions by iterating the model. And this does work in theory, but not in practice in the sense that when you iterate, you amplify even small errors in your one-step predictions. And because your longer step longer term predictions are policy dependent, then finding the policies um, involves branching and really exponential complexity in just for computing the consequences of your behavior in this iterated one step way. So we really need direct models that will take a way of behaving and jump to the possible consequences. And so many of our existing methods uh, are really uh, stuck in this trap because um, if you're if really the most clear way to think about it, the most compact way to think about it is that the state update process should be restricted to the fast part of the mind. It should not participate, for example, in the model or in planning in any way. Uh, if your model involves observations, then when you imagine futures, you have to simulate all the observations, and you have to imagine your way on your walk to work. You have to imagine every step of the way and everything that you might see and how you might react to what you would see and how the state update process would change as a function of what you see. It's it it's a trap because it forces you to go down to the micro level in order to make a long-term prediction. Now, i- just saying options is not a panacea because you still have to come up with the options. And a wonderful option, a useful one like opening the door, picking up the object, walking to work, taking the job, where does that come from? You still have to discover them, and it's quite a challenge to to find the right options. I don't want to minimize that. So as part of not minimizing it, so suggest some ways that it might come about. It might come about because the agent poses subproblems, like opening the door. If the door being open is an important state variable that it's determined to be important, then it might become a good um, uh, goal for a subproblem whose solution will be an option. And this is, when you formulate it in this way, then finding the options becomes a normal reinforcement learning problem. And finally, you also need the models of the options. And the models of the options, once you have the options, can be learned in a fairly straightforward way, either by Monte Carlo methods from the start and stop states. I started my option here and it ended there, so I could learn that. Or you can use temporal difference learning methods where you learn from your updated predictions on every step in an online incremental way. It would, of course, have to be off policy in general. Okay, so moving on to the fourth big challenge um, is that of course, we need to do with approximations because It's useful to consider the ultimate reason for this. And the ultimate reason is that the world is huge. The environment is huge. It's much bigger than the agent. Um, even for the agent to have in its mind a single state of the world is way too big, right? The state of the world, the position of every elementary particle in the universe, you could never, even if someone told you all that, your brain is not smart, your mind is not large enough to contain it, and it can't be because, well, the world contains many other agents, and what's going on in their minds is part of the world, and it's important to you, and so there's no way that we can have anything close to a complete understanding of the world. Um, and that's the state of the world. And so to know the dynamics of the world, that's roughly the square of the state. And so we cannot be exact, and we should embrace and recognize this and embrace it. So at a minimum, our estimates are going to be not true. They're going to be uh, greatly simplified, and they're going to have errors, and those errors will be permanent. They will not be something that, with as time goes infinity, they go away. They will remain forever. Okay, so notationally, our value function v of s is going to become a deterministic function v hat of s, and the part that will vary will be the weight vector w. So it'll be some high dimensional weight vector, maybe the weights of a neural network or some other um, learning algorithm that has parameters. And of course, then the model will also have to be parametric and approximate. So how are we going to manage this? Well, it's actually, again, not too, if we're careful, it's not too tricky. It's not too unclear how it's got to be done. So here's again, conventional value iteration is the first equation, our old familiar equation. Now we're going to make some changes. We're going to change the things shown in red. So the new approximate value iteration will not change the values, it will change the weights. The weights will be moved towards um, the same sort of expression, a max over possibilities. Instead of using the tabular value function, we'll have the approximate value function of the next state. And we'll have to use the gradient, uh, the, the gradient of that function with respect to the weights in the update. So that's what turns this equation into a vector equation. First bit is a scalar, and then the gradient as a vector. And so, the gradient just says, well, how would a change in the weights change the value function? And um, the scalar part said how the value function should be changed, what direction it should be changed. And so then it's natural to multiply the error times that gradient. So that's, you know, roughly how it has to be the direction for embracing approximation. How to do it practically and how to do it in a large scale is 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 critical. Uh, Particularly the search control becomes critical now. You're not just going to enumerate the states, you're going to have to generate the states to think about. But I want us to particularly focus on the innermost part, the computational costs. So if we think about the computational expense of doing this equation over and over again. This is the operation that I like to call a backup. It's an approximate backup at state S. And so recall that in validation, many states have to be backed up, and probably many times. So there are two outer loops in classical value iteration. The first loop is over all the states. And then there's another loop that says many times, go through the states many times. And we can't do that, of course. I've just said the number of states in the world is way too large. We're going to have to be them carefully. We're going to have to select them carefully. Um, but let's assume we're doing that. We're thinking about we found a way to make our thought processes relevant and progressive, adding to what we know and improving our policy and value function as we go. Or at least we're always trying to do that. Um, now let's also consider the complexity within each backup. Um, so, we, so within each backup, there are also two loops. Remember those the two loops, one for the max and one for the sum. So if you have if the max is a problem, if there are many options or actions, but you could do it incrementally. It's a research topic. I actually have a student working on it now, but um, you can do it incrementally. Um, the, s- the sum uh, is, I think, a more pressing problem. We may not have very many actions, but we're certainly going to have many possible next states because, yeah, if you do something, many things can happen. Maybe they happen with small probability, but many different things can happen no matter what you do. And if what you're doing is an option, then also there are many different possibilities over a long period of time about what will happen to all of your state. So we have to ask if the expected value, well, it's this, it's the sum shown in orange here. This is the expected value of the action. We're contemplating doing this action. We're trying to compute the expected value of it. Can we compute that in an efficient way without really having a sum over all possible next states? Because in general, that's a huge sum. So let's just think about that. That's the fifth challenge. How can we do those stochastic? If the world is deterministic, it's no problem. Well, if only one thing is going to happen, then you can say, oh, this one thing will happen. You can look at its value. There's no this sum is degenerating into a simple operation. But really, the world is very stochastic. There are lots of possible next states. And what are we going to do with that? Well, one way is to have a model that returns a sample of the next state, and then you could average over many samples. Okay, so it becomes incremental again. You could do one sort of sample backup. Um, that is an interesting idea, um, but I can't quite see how it combines with all the other things we want to do. Um, and without dwelling on it, it deserves more thought. Um, but what I'm going to conclude is that I don't know. I'm going to say I don't know if that's a good way. I see challenges in it. So we can talk about that in a minute as I finish. Let's consider, because I want to bring up this other trick, and that's involving expectation models. So this trick works exactly if the world, if the value function is linear. So suppose, as suggested by this lower equation on the left, that the value function, the approximate value function v hat, is just an inner product. The transpose indicates inner product between the weights and a feature vector for the state. So S, this bold S, is a feature vector for the state. And for the value function to be linear, it means the value is basically the inner product of that feature vector with the weight vector, a weighted sum. So I want to compare now an expectation model with conventional model. The conventional model, you recall, gives you a probability distribution over all the possible next states. Now we're going to treat our states as feature vectors. So we're going to input a feature vector, the bold S, and we're going to produce as output um, S bar, which means the expected next state. I'm not going to tell you all the individual next possibilities. I'm just going to tell you their average of the possible things, their expectation. So my model no longer produces p hat, it produces S bar. And so this might seem like it's not enough. I'm not telling you all the things that can happen. I'm only telling you their average. But the simple proof that's shown here um, in the black equations um, shows you that it is equivalent to actually having the full probability distribution in the case when the model is linear. So maybe we can talk through this simple proof. The first part on the left side of the equation, is the expected value that we want to compute. And yeah, I guess that expectation that's shown in orange, that process again has just been written here. And now v hat for s prime, that can be written as an inner product because the value function is linear. So we can replace the v hat with the inner product, s prime, with the weights. And then now we can group s prime with the sum. Just by grouping it differently, the sum uh, now is a vector, and it's so we can form that complex vector before we do the inner product. And that complex vector, well, what is it? Conceptually, if you think about what it is, it's the sum over possible next states and then the weight vector for that state. Well, that's the expected weight vector. It's the expectation of the next state, given that we're in this state and we do this action. And that is exactly what the expectation model gives us. It gives us that expected feature vector. And so we can achieve the result, the expected action value, just by taking the inner product of the S bar from the model with the weight vector. Okay, so what you might be asking, if this trick of using an expectation model and a linear value function, would it work with when I combine it with all the other things that I've talked about today, like options and average reward and the state update equation? And the answer is yes, everything does go, seems like it basically goes through. You might also ask about the restriction to linear value functions. And might that be unsatisfactory? It means we've not achieved um, generality and scalability. I'm basically going to think not. Um, it's not entirely clear, um, but I think it doesn't rule out. It doesn't rule it out. It doesn't mean we failed yet. Um, it remains a possibility. Um, and then there's the issue of using a sample models. Could you learn a sample model? Is that a practical way going forward? And one of the issues, which is, I think, which may be clear, is that I don't think we can learn sample models of options in the same kind of incremental ways that we do with expectations. Um, yeah, definitely not. Maybe it's too strong. Um, can we make the sample model method work? I think it's not clear. I think it's a viable candidate, just like the expectation models are a viable candidate, and we need more work to figure it out. So that's where I'm ending up. If I was to make a guess at a full solution, I think I would plunk for the expectation models with linear value functions, and using feature creation to enable the value function to be linear. Um, we do get to uh, choose the state update function, and that will determine what the features are. And if you have complete control of the features, you can make anything linear. Um, and so I think that is maybe the way forward. The model should also be heavily annotated with metadata, with things like how confident am I in this expectation, and how useful do I think this it will be to use this part of the model. And remember, we will need usefulness measures uh, anyway in order to do search control. Um, and uh, so remember also that uh, useful models are rare. The agent has to search for them, and that searching is not like filling in a table. Some things are filling in a table. Once you have the options, filling in the model is estimating known quantities. But finding the option models is more like mining or search, where the gold is the options whose approximate models are useful. This becomes a focus. The options, they provide the semantics, they make the learning problems well defined, but finding useful options, discovering them, must be done by experimentation and remains a challenge. So I think I'm basically done. I just want to remind you of the basic perspective, or what we've seen today, what I've learned by thinking about these things, is that planning is subtle, surprisingly unsolved, particularly in this case of stochastic dynamics. And there are these grand research strategy decision points in planning. We have to be aware of these. You don't have to choose the way I've chosen, but you have to choose. And this is a grand quest. We want to discover knowledge and learn it, and we want to use it effectively. This is reaching for reason in our AI agents. So, given this ambition, we should be um, our vision should be ambitious, and yet we should s- strive to be scientific and make our progress incremental. Thank you very much for listening.